And now, next speaker is Maciej Denkowski from Krakow, Poland. Maciej?
Yes, I'm here. Thank you very much.
Here.
Okay, so перш за все, я хотів би подякувати вам за можливість представити свої результати на цій конференції, на якій я беру участь перше. Мені дуже приємно. Дякую. But of course now I switch to English. So what I'll be talking about is the inner semi-continuity of medial axis and conflict sets. And this is a joint work with my former PhD student Adam Białożyt and my wife Anna Denkowska from Krakow University of Economics. And so let me start from the basics. What do we understand by medial axis? I think that in Ukrainian it is Herednia Wieś, probably. Anyway, the basic notions. So we are in the Euclidean space, Rn, as you can see here, and we consider a non-empty closed proper subset X here, and we pick a point A. For this point, we will be computing the Euclidean distance, d of dx of A, dx. We will use these notations. And we will be interested in the set of closest points to A in X. This set of closest points is denoted here by M of A. And this, of course, defines a multifunction, right? A multifunction whose multi-valuedness set, which means the set of points for which there is more than one closest point in X, is what we call the medial axis, or sometimes skeleton, of the open set that we get by taking the complement to X. Of course, more often we will speak of the medial axis of X itself. This notion was introduced in 1967 by Harry Blum in his paper on, this is actually a paper which is basic for pattern recognition in computer science. You will see why in a moment. So the first remark is that by the strict convexity of the Euclidean norm, it is easily seen that the medial axis has always an empty interior. But of course, there is this nice paper of Fremlin, Skeletons and Central Sets, from 1997, where you can find an example of a medial axis whose interior is non-empty after taking the closure. So if we want to somehow avoid topological pathologies, we should tame the topology, tame the geometry, and the right setting for this, we will see in a moment, is semi-algebraic geometry or minimal structures, subanalytic geometry. But since Bloom, as I said, the medial axis is a basic tool in pattern recognition. So here you have an example. Take a bounded domain omega, and X, its boundary, right? If we consider the part of the medial axis that lies inside omega, so this is denoted by S, and when we know S and we know the distance function to X along S, this suffices to reconstruct the shape. So that's the idea, and you see here that we have a kind of data compression, right? But of course, I'm not interested exactly in this application side. My work is more theoretical. So one more remark, just to better understand the notions, is that, of course, we know that the distance function is one Lipschitz. It implies that the squared distance function is locally Lipschitz. And therefore, by the usual result, the Rademacher theorem, both functions are almost everywhere differentiable in the Lebesgue sense. So in particular, the set of differentiability points of the squared distance function is a dense subset of Rn. And we have two results that, let's say, tell us something about the structure of the medial axis. The medial axis is empty precisely in the case when we started from a convex set. So if and only if X is convex, this is an old result even before the notion of medial axis was introduced. It is due to Motzkin. And another result that was stated in, well, different ways by Francis Clark, or then it appears in Yomlin without a proof, and in my paper with Lev Breyer, we have a general proof. The medial axis is exactly the set of non-differentiability points of the squared distance function. And besides, you see here that we can even compute the gradient, and the gradient is continuous. So this gives us some insight into the geometric structure. The medial axis is a projection, therefore, of the ridge that you get when you consider the graph of the distance function, right? And another closely related notion that it is definitely easier to handle, and often in the proofs we use not exactly the medial axis, but rather this one, the central set. It is defined to be the collection of all the centers of maximal balls. A maximal ball being such a ball outside X, so I mean not meeting X, a ball that you cannot put inside a bigger one, right? Without crossing X with this bigger ball. So of course, when you have a maximal ball, then its radius is exactly the distance of the center to X. And the next theorem is what actually accounts for why the central set is often used instead of the medial axis. It lies exactly in between the medial axis and its closure. One example, or two examples that show that both inclusions may be strict. So the first one is just a parabola. For the parabola, it's easy to see that the medial axis is a half line stopping at the focal point. But the focal point is a point for which the unique closest point is zero, right? The apex of the parabola. So the central set here is the closure exactly of the medial axis, and this closure is different from MX. And another example due to Chazal and Soufflet is a sphere with a tunnel like this. So in this case, you see here that the point, which is in my picture a blank dot, this point 0.001/2, belongs to the closure of the medial axis, but is not in the central set, because if you take a ball centered at this point, you can increase it to the bigger one seen on the picture. So both conclusions are both inclusions are strict. So let's turn to the first main result concerning the stability of the medial axis. What I mean by stability will be made apparent in a moment. Since its introducing, the medial axis has been known to be really unstable, in the sense that the slightest deformation of the set X may lead to a big deformation, a big explosion for the medial axis. You see here. So if we start from X, just a circle in the plane, the medial axis is the center, and you modify the circle by adding the smallest smooth protuberance, and you get obviously a medial axis that is actually a whole segment. So there is a big change in the structure of the medial axis, and this, of course, from the applications point of view, is a problem. It's a problem. It was investigated to some point by Chazal and Soufflet in their paper that you see here. And actually, they give this example. This is a typical example of what happens. And they showed some stability for C2 deformations by map images. But the main problem in this approach, this kind of approach that you have here on the picture, is that you have an initial state, and the final state, and nothing in between, and there's a black box, right? So it doesn't really reflect the usual notion of what a deformation is. If you see instead of this, the deformation is a continuous process, then you can extract some kind of stability of the medial axis, which may seem strange, but when you think really of the deformation as a continuous process, you will see that there is a stability, and this, the best way to express this is to use the so-called Pełne-Kuratowski convergence of closed sets, which is known and used in particular in optimal control, for instance. So let us define this notion. Consider a multifunction again. A multifunction, so a function that assigns to a point a set, right, of some fixed space Rn in this case. The domain of a multifunction is the set of points that yield a non-empty set f of x. And of course, we may identify any multifunction with actually a subset of the product of the two spaces, right? And the values being the sections, the vertical sections, and the domain being just the projection of the set f, right? The sections are denoted here fx. And we'll actually be using the sections rather than the multifunction. So the Pełne-Kuratowski lower and upper limits are defined at some point A. A, of course, should be an accumulation point of the domain in order to give some nice notion, right, of lower and upper limits. So these are defined, as you can see here, in the following way. These are sets. So a point Y from Rn belongs to the lower limit whenever you pick a sequence in the domain of f converging to A, you should be able to find points in the corresponding sets, in the corresponding sections that will converge to Y. And we will say that Y belongs to the upper limit if for some sequence in the domain, you are able to find points from the corresponding sections, from the corresponding values of the multifunction converging to Y. So of course, from the definition, you see directly that there is an inclusion between the two sets, right? It is easy to see that both sets are closed and that they do not change if you replace the initial multifunction but by the multifunction obtained by taking the closures of its values, right? It's purely topological fact. In case both limits are the same, let's say equal to some set E, we will speak of convergence, of the Kuratowski convergence, and this will be denoted, as you can see here, either by an arrow with a K, or simply writing this as a limit, right? And we say that the multifunction is inner semi-continuous at some point if the value set at this point is contained in the lower limit of f of x. Let's see an example of an upper limit, because we will be using in a moment this set. The usual Peano tangent cone. The usual Peano tangent cone is something that you obtain. So when you fix a point in the set x, A is a point from x, and you approach this point by a sequence taken from x, and you look at the seconds, the line seconds, and they stabilize. They stabilize the direction at which they stabilize is a vector tangent to x. This is exactly an upper limit in the Kuratowski sense of the translation of x to A and dilated by 1 over epsilon when epsilon converges to 0. Okay, the main theorem. First main theorem in the simplest version. So the story that lies behind is that I needed this result for some considerations from singularity theory in a paper written jointly with Lev Bilbrail from Fortaleza in Brazil. And the first version of this theorem was actually for definable sets in nominal structures, for instance, for semi-algebraic sets. Then we extended the result with Anna Denkowska to the case of conflict sets. I will speak of it in a moment. And then with my PhD student, we further carried this over to Riemannian manifolds and actually get rid of this definability assumption. So this is a general results, no assumptions on the geometry of X actually. So the only thing that we assume, so as you can see here, we take a set X with vertical closed sections. We assume that 0 is an accumulation point downstairs, right? And we assume that we have a continuity at 0, right? The sections are continuous at 0. So we are looking in the sections at the closest points to the sections xt. And MT, yes, I see now that I omitted, well, okay. I omitted one more notation, but it doesn't matter. MT is just the medial axis of the section at T. Then the medial axis of the limiting section has to be a subset of the lower limit of the nearby medial axis, the medial axis of the nearby sections. Of course, here there's one thing that we should be aware of. 0 could not, well, M here is, yes, M is the union of all the MTs, right? Above each T we have MT, and we take the union to get a set in the product, in the Cartesian product, right? So we project this set. What could happen is that 0 could not be an accumulation point. In this case, we posit this limit inferior to be the empty set. And if this is the empty set, then of course the theorem also holds, and it means that M0 has to be the empty set. This also has some additional information. And this result is the best one we can obtain in terms of stability, as we can see from this simple example in R3. So the parameter space is one-dimensional, is this axis T. The sections live in the plane, right? And we have this X. X is given by an equation. Each section at T is actually the graph of the modulus, but of course with the two branches that change, right? They are steeper or less steep. On the positive side, they are upwards. On the negative side, they are directed downwards. So you can see here on the picture that for each T positive, you get a medial axis that is always a half line ending at the origin. On the for negative T's, it's again a half line, but on the other side. So the limit inferior is just one point. It is the only point that you can reach by sequences, right, from both sides. While the medial axis of the section at 0, which is just the graph of the identical equal to 0 function, right, is empty because it's a convex set. So this shows that we don't really have a possibility of obtaining a better result. So the theorem that we have here, as I said, was the first motivation actually was from singularity theory, and I will show you the application. But first, some background for the application. It is known since Nash that when you have a smooth submanifold, smooth means CK smooth for k at least equal to 2. K could be infinite or omega meaning analytic, right? So a smooth submanifold has always a neighborhood in which the distance to this submanifold is uniquely realized. There's always a unique closest point. And the resulting function here, m of x, is of class ck minus 1. If the class was finite, there is a drop in the class. And the theorem is no longer true for k equal to 1. For k equal to 1, you have here an example due to Kratz and Parker of a function that is at the origin it is C1 but not C2. And indeed, it is computable directly that the medial axis goes down to this apex of this parabola-like graph. So let's introduce for a generic set X the set of CK regular points, by which we mean those points in the neighborhood of which X is a CK submanifold, and the complement is what we call the set of CK singular points. Here you have an example that actually you can always produce even an algebraic curve on the plane with a point that is CK smooth but not CK plus 1 smooth. This is an example. It's just a question of it's a simple fact. And one of the questions in singularity theory is a rather new question. It goes, well, it has less than 10 years, maybe slightly more, is to characterize the points of the points of X that are reached by the medial axis. So by this Nash result, we know that we have to look for them among the C2 singularities. But of course, you have here some examples that not all the singularities are reached by the medial axis. The first example is a set for which the origin is a C1 singular point while the medial axis is empty because the set itself is convex. In the second case, you have a curve for which 0 is a C1 regular point, but not C2 regular, so a C2 singularity, and still the medial axis stays away. Here above, in this Kranz-Parker example, you had a point that is C1 regular, not C2 regular, so a C2 singularity, that is reached by the medial axis. And among yes, here we have the natural setting for the question, same geometry, or minimal geometry, subanalytic geometry. You may think always of it as a variant of what we call semi-algebraic geometry, where we are interested in studying the geometry of sets defined by finitely many polynomial equations and inequalities. And one of the main tools in this setting is what we call the curve selecting lemma. If you have a definable semi-algebraic subanalytic set and the point in its frontier, then you can always find a continuous curve. And actually, I should have added here because this is important. This curve is homeomorphic onto its image. It doesn't reduce to a point because otherwise this curve selecting lemma doesn't make sense, right? It doesn't reduce. It's homeomorphic onto its image. It's a true curve that we can imagine, and it passes through A, and half of it, right? One branch is inside E. That's the idea. And the consequence, for instance, for this is that when you pick a semi-algebraic, let's concentrate on the semi-algebraic case, a semi-algebraic set, the tangent cone that we already observed is an upper limit, is actually a limit because you can move along curves. So when you need to obtain any sequence, you use the curve. So this is a limit, and this observation, which is not true in general, but is true in this nice tame geometry setting, makes possible the application of the main theorem to get what we call the tangent cone criterion. And the tangent cone criterion is the following. You take a semi-algebraic set, right? Suppose that it passes through the origin. And suppose that the tangent cone at the origin, denoted here by V, is non-convex. So its medial axis is non-empty, right, by the Motzkin result. Then the origin is reached by the medial axis of X, and moreover, the tangent cone to the medial axis at 0 contains the medial axis of the tangent cone, which itself is actually a cone. And again, this is the best what we can expect. Usually there's no equality, so let's have a look at the central picture. The central picture is the set X, a cone together with a cuspidal revolution surface. So the medial axis is just the line without the origin and this kind of skirt, right? On the left picture, what do you have? You have in green, the tangent cone to X. So the tangent cone is the upper part, which is already a cone, and just a line below. The tangent cone to the medial axis is, I'm sorry, it's not the tangent cone. The thing in red is not, it's not the tangent cone, it's the medial axis of the tangent cone. So we have to first look at the tangent cone in green, right, and construct the medial axis of it. The medial axis is just the axis for the upper part and a dual cone, actually, without the vertex. And on the right-hand side, you have the tangent cone to the medial axis mx. So it consists of a line, the whole line together with this conical thing. And you see that this is indeed the MV here on the left-hand side is a part of the whole tangent cone in the yellow on the right-hand side. And the proof. So by the curve selecting lemma, we know that the tangent cone is the limit of this kind of dilations. By the main theorem, we know that we have this inner semi-continuity, and the only thing we have to do is to understand what are the medial axes of the dilations of X. And by homothety, nothing else, we see that the medial axis of the dilation is the dilation of the medial axis of X. And again, you get something that is definable, and by the curve selecting lemma, when you take the limit inferior, you get exactly the tangent cone. So this gives us the inclusion. But then by the Motzkin theorem, since we've assumed that V is non-convex, we see that there is that the medial axis MV is non-empty. It is a cone. So it is a cone with vertex at the origins. So we get exactly what we wanted, and that's the whole proof. So some other applications of this that can be found in what my PhD students produce. Here you have some bibliography. Let's skip this and move to now the most general version of the theorem, which I would like to explain, and then finally explain what are the conflict sets. So the most general result concerns the Riemannian manifold. And a Riemannian manifold, of course, that we will assume to be complete, so as to have a possibility of apply the Hopf-Rinow theorem. And the Hopf-Rinow theorem says that you always can join a point from the manifold to its closest point by a geodesic, right, of exactly the minimal length. So omega xp is the set of all geodesics originating at P and going to the closest points in X. So these geodesics will be denoted if we really need this notation by xp. So now the medial axis is defined like this. There are two different geodesics, right? It's exactly what we have, and the central set, which was actually crucial in the proof of the simple version, is replaced by what we call the cut locus. The cut locus, as you probably all know, is the points for which the geodesic ceases to be the shortest path, basically. And as we had this sequence of inclusions with the central set, we have exactly the same with the cut locus, and this is a result due to Albano, as far as I know. I mean the second inclusion, because the first inclusion is actually obvious. There's nothing to prove. And we introduce also a space of parameters, capital Pi. This is a T1 topological space with a distinguished non-isolated point 0, and we assume that this point has a countable basis of neighborhoods in order to be able to use sequences and nothing else. So the main theorem is what we have here. If we have a family of closed sets parameterized by T, and this family is continuous in the sense that xt converges to x0 in the Kuratowski sense, and we introduce this M. This M is just the set whose sections are the medial axis of xt. Then we have exactly the same inner semi-continuity. Exactly the same statement. So now we are ready to pass to the conflict sets. What are conflict sets? It's a very close notion. You start from a finite number of pairwise disjoint non-empty closed sets, x1 to xk, at least two of them. And the conflict sets is the sets of points. So we keep this Riemannian manifold set. Is the set of points for which we are the closest to at least two of the sets, right? So rho of p here is the distance to the union of the sets. Okay, it is also useful to introduce the notion of territory. The open territory of a set xj with respect to the family X is the set of points that are closest to xj than to the remaining set. When you take its closure, it has this nice description with a weak inequality that you see here at the bottom of my. Oh, I'm sorry, of my page. So clearly, the conflict set may be also obtained as the union of these closed territories intersecting 2 by 2. It's the common boundary, actually. It's the common boundary of the territories, of the open territories. So one example to better understand the usual one. You take a point, a line that doesn't pass through that point. The conflict set is just the parabola, the usual construction of the usual geometric construction of the parabola as the set of equidistant points to a line and a point outside the line. What is the relation to the medial axis? Is what we have here. The medial axis of the union of the sets is the whole conflict set together, and all these unions here are disjoint, together with the medial axis of the different sets, but not whole of them, just the parts that lie inside the corresponding territories, which is actually this lemma is a simple exercise, nothing else. If we have the sets reduced to singletons, then the conflict set is exactly the medial axis of these singletons put together, and this is what we call the Voronoi diagram. Voronoi was actually a Ukrainian mathematician who was a professor at the Warsaw University in the 19th century. It's a notion that it is really it has really some nice applications, not only in computer vision, but also in biology, geography, this kind of things. And of course, for the Voronoi diagrams, we have the inner semi-continuity by the previous result, while for the general conflict sets, we have to actually prepare something. And I'm almost done. So we assume that we have several sets now parameterized. You see, there is this parameter space again. The sets in question have a common projection that will be denoted somehow. The common projection below, you see, at the bottom is denoted by pi tilde. And we assume that in each case, well, yes, in each case, it's exactly the same projection. So we can approach zero, but you see, zero is a new point somehow, right? We will be interested in the limiting behavior of the sections. We do not assume that zero gives you a section, definitely not. But we assume that all these sets converge, right? We have converging sections. The limit could be empty. I should have maybe added that this Kuratowski convergence is a generalization of the Hausdorff convergence, but to sets that are only closed and that could be empty, not compact like in the Hausdorff case. And then what we do next? So we consider the union of these families actually. So this union, it is a disjoint union by assumptions, has convergent sections to the union of the different limits, right? But now observe that this union may no longer be disjoint. The limits can overlap. And we have to cope with this. So what do we do? We will want, the idea is that when we want to study, as you can see here, the limit behavior of the conflict set of these families parameterized by T, we first of all have to understand what is the limit family, because as I said, the different limits may overlap. So the idea is that when they overlap, we will have a problem to define a conflict set, right? So it's natural to put together the sets xt for which the limits will overlap. So we have to regroup somehow the families and keep track of what happens with the corresponding conflict sets. A canonical approach to do this is the following: we'll identify those sets xi and xj for which either the limit is empty or overlaps, but in a specific way. You see, the two limits may not overlap, but we can join them by consequently overlapping limits. Okay, that's the idea. So they don't overlap, but they form something that is a sequence of overlapping. So this is an equivalence relation, and of course this gives us a regrouping of the initial sets, and we still have the convergence of the sections. And now this is what is written here. Is we have this regrouping, and we consider the conflict set. So the conflict set CT of the initial family, the conflict set CT tilde of this regrouped family of sets, and C0 is the conflict set of the limiting family, but as I said, some of the limits could be empty, so we get rid of them first. And of course, there's another possibility. This family could be either empty or could consist of only one set. In this case, we assume that the conflict set is just the empty set, which is pretty obvious. The first lemma that we have here gives us a relation between this regrouped family conflict set and the initial conflict set, we have an inclusion, which is nice, and this holds for any t. And the second main theorem is actually two parts. The first part is just the inner semi-continuity. So on the right-hand side, you have the lower limit of the conflict sets, of the initial conflict sets. On the left-hand side, you have the conflict set of this family that you obtain from regrouping the limits in a nice way, right? And actually, when we replace the initial family xt by the regrouped, the corrected family with the tilde, you get even a continuity result, you get convergence. So this has some consequences for instance, in economics. It was used, I don't, but I confess that I don't really know how it was used, but it was used, I know, by my wife, some economical things. So one last illustration that maybe will make the things easier to understand. So we start from 4 sets. The sets are just points. We have 4 points. So this point x1 that actually stays fixed, to simplify things. We have 2 points x2 and x3 that will move and merge. And we have a 4th point, x4, that goes to infinity, disappears at infinity. So for each t, you get in red the conflict set, the Baganoy diagram, right? It's this shape that you see here. But so we will want to regroup the 2 points that in the limit will merge, right? And we consider them as a unique set. So the new conflict set in yellow is the one with the tilde, is just this modulus shaped 2 things, right? And one of the lower one will disappear at infinity, while the upper one will become less and less steep, right? So C0, the limit, is just a line, and it is indeed the conflict set between the two limits. But if you look at what happens with the convergence of the initial conflict sets, the things in red, you have the upper part that becomes linear, and you have this lower part that disappears to give you a line. So this is the thing in purple. It's a bigger one, right? The lower limit is a bigger one, and that is all. And I think that I managed to stay within my time limit. So thank you for your attention. Dziękuję za uwagę. Ukraina peremorze.
Thank you. Let's send